Next, we will cover GARCH model, very important model in finance. So GARCH model, okay, here. So let's enlarge the file. Okay, I open the PDF file. So conditional heteroscedastic models. So what is the asset volatility? Okay, it is a conditional standard deviation of asset return. Here, it is important. It is a conditional model. So based on some information, thus when the information changes, the variable changes. So basically, it is standard deviation, time varying standard deviation, varying depend on the conditions. Why is volatility important in finance? Has many important application in finance. Volatility is very important. In option pricing, derivative pricing, in Black-Scholes formula, we need to estimate volatility in order to use Black-Scholes formula. Risk management again, we have to use estimate volatility like a value risk. Asset allocation, minimum variance portfolio, okay, like page 184, 5 Campbell Law McKinley, or interval forecast. In order to forecast interval, we need a volatility. When the volatility is high, the interval becomes wide. All right. A key characteristic. One problem is that volatility is so important in finance, but thing is that volatility itself is not directly observable. We can observe return, we can observe stock return, bond return, but we cannot directly observe stock return or bond return. That's a problem. So we have to estimate that. Then the question is how to calculate volatility. There are several versions of volatility, but conditional standard deviation is most by far the most commonly used. We can use possibly when use high frequency data like French Schwartz Stambau 1987 realized volatility or daily low return use intraday high frequency low return. So if we want to know what is the daily volatility, then in order to estimate daily volatility, we go intraday, like a minute by minute data, and then we estimate standard deviation, and then we extrapolate it, something like that. Or we can use a daily low, high, low closing prices, like range is daily high minus daily low. Or maybe we can use implied volatility option there, like a fixed or CVOE of figure 1. So where is the figure 1? Yes, this one. Time plot of daily fixed index from January 3rd, 2007 to April 11, 2014. Okay. Or econometric modeling, use daily or monthly asset. Now we focus on this third part. We focus on the econometric modeling first. Okay, use of high frequency data will be discussed later. Okay, note in most application volatility is annualized. So when you say volatility of Samsung Electronics stock, it is like annual volatility per year. This can easily be done by taking care of the data frequency. For instance, if we use daily return in econometric modeling, then annualized volatility is root 252 sigma, assuming we have 252 business days per year. We need a root because it is standard deviation, right? Where sigma t is estimated volatility or standard deviation derived from employed model. Now we use monthly return, then the annualization is now we multiply root 12. Again, here sigma t is some estimated volatility, estimated conditional standard deviation derived from the employed some model called the monthly return. Our discussion, however, continues to use sigma t for simplicity. Okay, basic idea of economic modeling. Shock of asset returns are not serially correlated but dependent, implying that the serial dependency in asset return is non-linear. Okay, as shown by autocorrelation function of return and absolute return of some asset we discussed so far. So basic structure is something like this. RT is suppose it is stock return. RT is mu t, some trending part, and the shock part AT. Here mu t is possibly depends on some ARMA model we learned. Some constant of 50 plus AR term, ARP, and then MAQ part. Okay. So we all know this information. It is constant, and then it is t minus 1 to t minus p. So it is already history we know. Again, it is also history we know. So this is a known part, mean. Volatility models are concerned with the time evolution of 80 part. So we are interested in sigma t square is basically variance of RT conditional on information up to t minus 1. Because we know mu t is all we say it's measurable, or it is basically those all variables are measurable, right? Because we know information at the time, so we can measure those values, those are measurable. However, AT is short, so we cannot measure it based on the information of yesterday, t minus 1. Therefore, volatility of conditional volatility variance of RT is the same to variance of AT FT minus 1. Conditional FT minus 1. FT is a set of information set. Okay, so it is fixed. The conditional variance, so written RT. Okay, so it is all about conditional variance. Okay. Now consider daily index of S&P 500 index from January 03, 2007 to April 13, 2015. The log return follows approximately an MA2 model. So RT is AT minus some shock part, AT minus sigma T 00112. Okay. So our demonstration is something like this. So series, okay, so M1 model residual, if we residual square, okay, residual, if we model the mean part correctly, then residual no pattern, but residual square is not being modeled. So residual square is very persistent. Okay, it doesn't die out quickly. Okay. Also, how about volatility? Is volatility constant over time? No. See the autocorrelate function squared residual. As you can see, it is very persistent. So we want to capture the time dependence of this squared part. Then the question, how to model evolving volatility? Two general categories. One is a fixed function, and one are the stochastic function of available information. Okay, so univariate volatility model discussed. Autoregressive conditional heteroscedastic arch model by Engel. Engel got Nobel Prize because of this. Now, generalized arch or GARCH model of Boloslev. This GARCH model generalizes this angle. Boloslev was the doctoral student of Engel. Okay, so students generalized his teacher's model and got super famous. Boloslev is also very famous. Now we have a GARCH M model, iGARCH model used by Risk Matrix. Risk Matrix is very famous, famous company, special on risk management. And then here, when they estimate volatility, they use iGARCH. And then we also have a very famous another GARCH, exponential GARCH, eGARCH model developed by Nelson, or threshold GARCH model by Jacquian, or GJL GARCH. Okay, this is my favorite actually, GJL GARCH. GJL model by Golston, Jagannathan, and Lincoln. A symmetric power arch model of Dean Granger angle. T-GARCH and GJL model are special case approach model here. And then we have some stochastic volatility model by Melino Turnbull, Harvey Louis Shepard, and very famous model. Now let's start very easiest one, arch model. Well, this is a thing. Okay, this is shock. Okay. Let's go back to here. So in the stock market, in the stock return, for example, here, well, this one is history. We know this one, but we don't know this one, and then we want to model the volatility. Standard of this one, 80 part. This is shock. And here, now we assume that AT is sigma t epsilon t, right? And epsilon t is the sequence of IID random variable with mean 0 variance 1. By multiplying sigma t is standard deviation becomes sigma t, right? And then we assume that actually model that sigma t, square of sigma t, which is because it's square, so it is the variance of AT, right? We assume that sigma t square is alpha 0 plus alpha 1, AT minus 1, blah blah blah. Okay, so this volatility is dependent on square of past shocks. This is arch. This is arch M model because we have M reg, where epsilon t is a sequence of IID random variable with mean 0 and variance 1. Alpha 0 is greater than 1 and alpha I is 0 and I greater than 1. Here, about the distribution of this, the most popular one is standard normal distribution. But sometimes we can use standard student t distribution or generalized error distribution or some skewed distribution. Now, properties of AR arch model. Consider an arch 1 model. Okay, so AT is sigma t epsilon t, and then we assume sigma t square is some constant plus linear function of one period ago shock AT minus 1. Okay, so this A t minus 1 and AT, right? There is one leg. Okay, where alpha 0 should be greater than 0 and alpha 1 is greater than 0. Okay, and then EAT is of course mean 0. We demeaned it because it is shock, it is error term. And variance of AT is alpha 0 1 minus alpha 0. Okay, where it is unconditional one. Unconditional. Okay, so by taking expectation basically, unconditional expectation, you can drive this one. Under normality, M4 look like this one. Okay, so we have 6 because of now we have time varying variation. We have 6 tails. So third property implies heavy tails. Okay, this one is heavy tails. Okay, so well, if we ignore this part, the stock return is normal distribution. But if we take into account that variance itself can be changing, the stock return has a heavier tail, thicker tail. Okay. Now, what is the advantage of this arch model? It is simple, and it generates volatility clustering, and it generates heavy tail, high kurtosis. Weakness symmetric between positive and negative price return, and restriction provide no distribution, not sufficient adaptive prediction. Okay. Now, building an arch model, modeling the mean effect and testing for arch effect. Okay. H null arch effect versus alternative hypothesis arch effect. We can use Q statistics of squared residual like McLaren, Lee, and Engel. Okay, and then next, okay, we squared residuals and then we determine order. For example, by using partial autocorrelation function or squared residuals. In practice, simply try some reasonable order like 1 or 2 in most cases, and estimate a conditional maximum likelihood estimation. Okay, basically we can estimate with Stera, Python, or R. Okay, they can do this very easily. Model checking, we can check the Q state of standard residuals and squared standard residuals. Square quarters square residuals. R provides manipulator for model checking and for presenting the result. Software, we use R with the package FGARCH. Other software is available. Estimation, conditional maximum likelihood estimation or quasi-MLE. Okay, we can use this technique. Okay, they have a good library. Okay, special note: in this course, we estimate volatile model using R package like FGARCH with GARCH fit command. Okay, so we can skip this part. R demonstration. This is very important example, so yeah, you can follow. Actually, what I think is that okay, I think we can do some simulation. So well, let's try. So ChatGPT. let me open ChatGPT and then simulate arch1 process with Python. Let's try. So okay, to simulate arch1 process, we need to follow a series of steps. Arch auto-regressive conditional heterostochastic models are used for modeling time series data that exhibit time-varying volatility. Here's how you can simulate the arch1 process using Python. Determine the model parameter. Alpha 0 is a constant term. Alpha 1 is a coefficient of lagged squared error term. Now generate error term and conditional variance. The error terms are drawn from normal distribution. It doesn't have to be normal distribution, t distribution, but for here, we use a simple model, normal distribution, with mean zero and conditional variance and their standard deviation. Now, simulate time series data. Okay, here's a Python code. Okay, so let's copy this code and let's run it. So collab research google.com/hashtag create new, and then we paste here and let's run. First run takes some time. Okay, so we import the numpy library and matplotlib library, and then we give random seed 42 so that whenever we run the model we have the same result. And alpha 0 is 0.1, alpha 1 is 0.85. We have so very persistent volatility possibly, and we simulate 1000 number of observation. Okay, and they initialize arrays to store the results. So for epsilon, we fill these zeros, okay, all zeros, and sigma to zeros, and we fill this reasonable number. Now generate arch1 process. For t in range from 1 to n, sigma to t is based on model alpha 0, alpha 1, epsilon t minus 1 square, right? Square. Here, well, it starts 1. So epsilon 0. Here, epsilon 0 is of course 0, right? And epsilon t is some normal distribution, and then is standard deviation. Square root is determined by this one, alright? So this is important. So the time varying, the variance is time varying, right? Square root, okay? Actually, standard deviation. We took root, so standard deviation. Now we can take a picture, then we have this one. Okay, so this is a simulated arch1 process, right? So where your variance, but sometimes it moves a lot, sometimes it moves less. And then next, simulated arch1 process figure epsilon, but I also want to see the sigma. Okay, hey, I want to see both epsilon, and then estimated volatility. Okay, sure, sigma 2. Okay, so basically same one. Okay, now yeah, if plot sigma. Okay, so let's copy the code and then delete this one and run code again. Okay, so yeah, this is the series. We squashed a bit. Okay, squash it. Okay, and then well, sometimes it move a lot, sometimes then the square the volatility is time varying. So when there is spike in red is a volatility, right? Volatility. When there is spike, it means it move a lot, right? So it seems that this blue red one and then blue one, well, red one is the volatility. When volatility high, blue move a lot, so it makes sense. Okay, so we simulated some data uh, by assuming Archer model. Okay, next. Now in reality, we when we simulated that we assume alpha 0 is 1 and alpha 0 is 0.1 and alpha 1 is 0.85. However, in reality, we don't know this number. Okay, so from this data, okay, from this we observe again the volatility red line itself is not observable, so we can only observe this blue line, blue data. So using this blue data, question is how can we estimate red one? Okay, from blue one we want to estimate red one. Okay, red one, in order to generate this red one, we need to estimate these parameters. Okay, so we can go to ChatGPT. Next, using the generated epsilons. Next, regard the generated epsilon as data, and then estimate arch 1 model. Okay, to match the actual model using a generator, we can use Arch package in Python, which provide tool for working the Arch model. Here's how you can estimate Arch model based on simulated epsilon data. Okay, so we have to install Arch. So code. So yeah, here now code. Okay, and then okay, we install. Actually, here we usually need this one. Okay, so let me do it again. Okay, same. Okay, done. Okay, so we install the library. Okay, and then okay, next go ChatGPT. Estimate Arch1 model. Okay, so again we can copy the code and then add code and then let's run it. Okay, so well, numpy mapper library, actually we already imported it, so delete it. So from Arch we import both Arch model and then np random seed. Here, okay, they start from generating the data, figure, simulate the Arch process. Okay, so we don't need this part, we already generated this data. Okay, so we don't need this part. Now AM is arch model, epsilon volatility arch, p order is 1, and we fit the model and print result summary. Okay, so this is estimate result. Okay, so mu is very close to 0. Okay, because there is no constant term in our model. Now omega is alpha 0 and alpha 1. This is 0 0.1, 0 0.7, about 0.76. So they are not exactly same to this one. They're not exactly same to this one, but close enough. Okay, and then next plot the estimated volatility together with estimated volatility together with original the original correct volatility. Okay, correct one. Okay, to compare now. So here again in the model we know this is the correct, we already said. Now we have to compare this one and then our estimated volatility here. Okay, so let's start everything again. Okay, so okay, So this is the original volatility. So simulate the archive process. So this is data. And the second is the original one. Third one is our estimated one. Okay. So this red one and green one looks pretty similar. So it means that our model is, well, not bad. Okay. Okay. We very closely follow the original correct model, which is actually unobservable. Okay, so we generate this data by assuming this volatility, and then indeed we capture this volatility well. Okay, there is no wonder because, well, as we said, our estimated process is estimated, the coefficient is very close to the original model, right? So it is not surprising in some sense. So here the fitted model, well, this is another example. A model checking statistics indicate that there are some high order dependence. So we can skip this part. If we use fitted model with sensitivity innovation, then we have this one. Okay. So if we compare with the normal innovation, so it is like a given data, data here, data all given. So if you use this data, then using a heavy tail lister absolutely the arch effect. The difference between model is small for this particular interval. You may try other distribution as well.